So you've chosen answer D, that the buoyant force is the same for all 4 balloons. And somewhat surprisingly, this is correct. The force of buoyancy we can write as rho times g times the volume of the object displaced. And the density in this case is the density of the displaced fluid, so the density of the surrounding air. It has nothing whatsoever to do with the fluid inside of the object that's displacing the air. What I find somewhat surprising is that there's a force of buoyancy actually acting on the water-filled balloon. And because the volume of all 4 of these balloons is the same, the force of buoyancy is the same for all 4. So if we did a free body diagram for each balloon, for the hydrogen balloon, for example, there's a force of buoyancy acting upward. But there's an equal force acting upward on the helium-filled balloon, on the air-filled balloon, and even on the water balloon. However, it's the fact that the weight of the water is so much greater than this buoyant force is what would cause the balloon to fall if this string were to break. What I find interesting is that if a force of buoyancy acts upward on this water balloon, because the human body is essentially all water, the consequence of this is that a buoyant force acts upward on all of us. And by my calculations, it's somewhere on the order of something a little bit less than a Newton of force acting upward on us. If we converted it to mass, that's about 70 grams, or something like a little over 2 floral ounces. And that's something like a quarter or a third of a cup of water. So somewhat surprisingly, the atmosphere does make us a little bit lighter because the air pressure at our feet is greater than the air pressure at our heads. And the net effect is to push us upward just a little bit.